Welcome, also on behalf of all colleagues in the project, to this video on the terrestrial networked positioning system. In this video we present the design and architecture of this positioning and timing system, and we developed a working prototype which has been deployed on the Delft University of Technology campus. We'll take you on a tour. And finally we present a selection of results from the experiments we carried out with the prototype system. The two main features of the system are first the distribution of an accurate time and frequency reference generated by an atomic clock in the red box, and do this over an optical fiber network shown in yellow, and second radio transmitters in the green squares, which are connected to the optical fiber and deliver wideband ranging signals to mobile users.
The atomic clock that we use is here at VSL, the Dutch Metrology Institute. Hi, Erik.
Hi, Jeroen. Here we are at the VSL Time and Frequency Laboratory. Here we make the Dutch national timescale with these 4 atomic clocks, and then the signal from the timescale goes into the optical fiber there in the back. So this is the White Rabbit groundmaster that transfers the Dutch timescale signal into an optical signal that comes out via this optical fiber. And then via this panel we go outside the building.
So the optical fiber goes from the atomic clocks here underground through a couple of data centers all the way to the campus of Delft University of Technology.
Here we are at Delft University of Technology, and specifically at the Green Village, an experimental site where we conduct our experiments. From the technical server room here at the Green Village, the optical signal is distributed to the radio transmitters. Antennas of 6 radio transmitters have been installed in lampposts and at rooftop corners of buildings. They replace, in this terrestrial network positioning setup, the GPS satellites, which each have to carry an atomic clock or even several ones. This is an overall impression of the experimental setup with the prototype system in a built-up area, representing an urban multipath environment. In the red ellipses at left you see 2 of the transmitter antennas, and in the yellow ellipse in the middle the receiver antenna fixed to a trolley. With this car we conducted kinematic experiments at low speed. In the middle you see the white antenna to receive the radio signals, and on the 2 sides prisms, optical prisms. They are used for the ground truth verification. These are positioned using robotized land surveying equipment and positioned at the millimeter level. This graph presents for one of the runs TNPS position errors with respect to the ground truth of the car. Using 20 MHz of bandwidth for the radio signal, which is commonly used in GPS, the position error is at the meter level as a result of multipath, that is by signal reflections on buildings around. Using 160 MHz of bandwidth, we gain almost a 10-fold improvement in position accuracy, which is now at the 1 decimeter level, as you can also see from the RMS figures given at right. Next to position, the TNPS inherently provides time. For this particular run with the trolley, for a duration of 3.5 minutes, we connected also the receiver to the optical infrastructure for verification purpose. So we see here constant clock offset due to equipment hardware delays, which can be calibrated, and the spread in terms of standard deviation is only 4 centimeters, or just over 1/10 of a nanosecond, which is very good. As already said, in urban environment, using a wideband radio signal is key to obtain these high accuracy positioning and timing results, and Gerard will elaborate on how we generate the wideband radio signal.
Here you see the demo setup in the lab. This is the timing node, which is fed with the optical timing signal. The 1 pulse per second and 10 MHz signals are fed to the USRP, which then is in a synchronized way transmits the OFDM signal, which can be either selected for 20 MHz bandwidth or 160 MHz bandwidth.
The project, carried out by Delft University of Technology and Vrije Universiteit University Amsterdam under the name of Super GPS, has been funded by the Dutch Research Council NWO. Partners in the project are KPN, VSL, OPNT and Fugro, and we also gratefully acknowledge the support by all those listed at the bottom of this slide, as well as the members of the project's user committee. Thanks for watching, and we hope that you enjoyed this video.